All right, welcome. Today, we're going to pull back the curtain on something we all use but almost never see, the high-stakes world of high-voltage electrical work. This is a world where there is literally zero room for error, and everything, everything, is about precision and procedure.
Just think about it for a second. The lights in your room, the phone or computer you're watching this on, pretty much our entire modern world, it all runs on this massive, incredibly powerful electrical grid. It's designed to be totally invisible. We don't even think about it. It just works.
Okay, but what happens when something needs to be fixed? When a real person has to go out and physically touch a piece of equipment that's carrying enough juice to power a small city? How in the world do they do that safely? Well, that's exactly what we're going to break down.
And the answer, you might be surprised, isn't just about wearing some thick rubber gloves. Nope, it's this incredibly detailed system that's built on three core ideas: a bulletproof plan for every single action, a super strict process for how people talk to each other, and just absolute uncompromising precision.
So first things first, let's really set the scene and talk about why all this is so incredibly important. The stakes here, they're as high as they get.
Yeah, the dangers are exactly what you'd imagine, and they are terrifying. We're talking about severe electric shock, horrific burns, life-changing or life-ending injuries. These aren't just, possibilities on a safety poster. They are the real-world dangers that every single rule, every checklist, and every single step is designed to prevent. Now, with stakes that high, you absolutely cannot have any confusion about who's in charge or who's doing what. So safety starts with a super clear chain of command and communication that has to be, well, perfect.
The best way to think about it is like air traffic control on a pilot. You've got two key roles. First, there's the control person. They're sitting in a control center, kind of like the air traffic controller, seeing the big picture of the whole network. They're the planner. And then you have the authorized person. This is your pilot. They're the one on site, with their hands on the equipment. The key thing is they work in perfect lockstep. The pilot can't do a thing without an order from the tower, and the tower relies on the pilot to execute those orders perfectly.
And that brings us to the plan itself, because in the world of high voltage, absolutely nothing is improvised. You don't just wing it. Every single action is scripted out, down to the tiniest detail, way before anyone even thinks about touching a switch.
And that script has a name. It's called a switching schedule. It's basically a document that lists every single step in the exact order it needs to happen. What's so smart about this is that it takes the pressure of making complex decisions off the person in the field. Their job isn't to figure things out on the fly. It's to follow a pre-approved, double-checked plan to the letter.
And look at how they communicate. It's this brilliant, simple system. First, the control person explains the big picture goal. Then they give a very specific instruction, like open breaker 1, 2, 3. Now here's the crucial part. The authorized person has to repeat it back, word for word. Roger, opening breaker 1, 2, 3. Only then do they actually do it. And after they've done it, they report back. Breaker 1, 2, 3 is open. It's a closed loop. There's just no room for mishearing or misunderstanding.
And I just love this line from the actual procedure. It says they shall pause to consider the consequences. This isn't just a checklist of mechanical actions. They build in a mandatory pause, a moment to just stop, think, and recheck. It shows you that this is about a mindset, a culture of deliberate thought, not just flipping switches.
Okay, so the plan is in motion, the communication is perfect, the circuit is isolated, the power's off, so we're safe now, right? Nope, not even close. And this is where the next and maybe most important layer of safety comes in.
Yeah, this is a huge misconception for a lot of people. You might think, hey, if you flip the switch off at both ends of a power line, it's dead. But that's just not the case.
The thing is, a line that's supposed to be dead can become lethally live in a split second. Someone somewhere else could accidentally turn it back on. A generator somewhere down the line could start feeding power back the wrong way. Or, and this is a wild one, a nearby live cable can actually induce a dangerous voltage in the dead one just through its electric field. It can come alive with absolutely no warning.
And that is exactly why you have to apply what's called a primary earth, or a ground. It's basically a big, heavy-duty cable that you physically connect from the dead equipment straight into the earth. So now if that line does accidentally get re-energized, all that deadly electricity has an easy, safe path to follow, straight into the ground instead of through a person. It's the ultimate belt and suspenders safety plan. Isolating the power is the belt, grounding it is the suspenders.
All right, so we've got our plan, we've isolated the circuit, we've even grounded it just in case. But what if you're not 100% sure you have the right cable to begin with?
Imagine you're in a muddy trench, looking at 3 identical black cables. This leads us to what is, without a doubt, the most dramatic safety check of them all.
Seriously, picture it. You're in a trench. There are a bunch of thick, identical-looking cables running side by side. The plan says you need to cut into circuit 4B. But they all look the same. Pointing at the wrong one isn't just a mistake, it's a fatal one.
So how can you be 1,000% certain that the cable you're about to cut is the right one and that it's truly dead?
Well, the logic is kind of brutal, but it's genius. You prove that it's dead by trying to kill it.
It's a procedure called spiking. The operator attaches a special tool, a spiking gun, to the cable they've identified. Then, they get to a safe distance and remotely fire a sharp metal spike right through the center of the cable, trying to short-circuit everything inside. Now, if they got the wrong cable, if it was secretly live, there would be a massive explosion of energy right at the tool, and the system would trip out. But if they got the right cable, the one that's properly isolated and dead, what happens? Absolutely nothing. Just silence. And that silence is the final, undeniable proof that it is safe to work on that cable.
So when you step back and look at all of this together, you start to see it's not just about one single safety gadget. It's about building layers and layers of redundancy, where each step backs up the one before it.
You've got the people, a clear command structure so everyone knows their role. You've got the plan, that pre-approved script for every single move. You've got the process, that physical safety net like grounding to protect you from the unexpected. And then you have the proof, that final, no doubt about it confirmation, like spiking, that tells you you're good to go.
And this final quote from the safety rules just sums up the whole philosophy perfectly. Be deliberate, neither rushing nor causing undue delay, and shall take nothing for granted. It's about finding that perfect pace. But most importantly, it's about a mindset where you assume nothing and you check everything. You just take nothing for granted.
You know, it really makes you wonder, doesn't it? What other huge, invisible systems do we rely on every single day that are governed by these kinds of meticulous, life-saving procedures? From air travel to medicine, there's this whole hidden world of professionals following strict protocols to keep us all safe. Hopefully, this gives you a little bit of a new appreciation for the incredible work and planning that goes into just keeping the lights on.